I'm honored. Cool, and also thank you everyone for showing up and attending the talk. Okay, so most of my work is on optimization and reinforcement learning, especially multi-agent RL. And that's exactly what we will be talking about today. I will discuss two of our recent works on multi-agent RL in the simple two-agent competitive setting. And the important contributors for both of these works are Dr. Justin Romberg, and also Dr. Tin Dong, who is an assistant professor at Virginia Tech. Okay, so I'd like to start by motivating the study of multi-agent RL a little bit. I mean, I'm sure we have all seen some successful application of reinforcement learning to real life. AlphaGo is a famous one, and also there has been a lot of active research on applying RL to robotics, autonomous navigation, education, healthcare, and other domains. And most recently, this ChatGPT, training of this ChatGPT has a little bit of RL flavor in it as well. But I would say most of these successes for reinforcement learning are primarily achieved in the single agent setting. But single agents, a lot of times, they're actually embedded in a much larger multi-agent system. So if you're able to understand behavior of the agents at this higher system level, you might be able to do to make better decision. So understanding RL, multi-agent RL is important. But so far, this is still much less understood compared with single agent. So there actually, in the recent 3 to 4 years, there have been many interesting works that study the structure of reinforcement learning in single agent setting, and utilize those structure to design provable and efficient algorithms. But a lot of these algorithms do not extend to multi-agent setting, or it's not clear how they will extend to multi-agent. So I mean, something you can do is, okay, you can make every agent in the multi-agent system deploy some single agent learning policy or algorithm. But the problem is, once everyone starts learning, the environment becomes non-stationary from the viewpoint of every agent, and you immediately lose all these convergence guarantees. And when I say multi-agent RL, I think of this as a broad concept. There are specific problem setups within multi-agent RL depending on how the reward function of the agents align with each other. Well, example is, okay, so if the reward function of the agents are very much aligned, or even identity, then they have the same goal and they will tend to be cooperative. And the dynamics will be very different from if the agents have completely opposite reward, right? In that case, they will tend to be competitive. You can also have reward functions being a mixture of identical and opposite, and that's even more complicated interaction. So you will probably need a specific tailored analysis, tailored technique, or tailored understanding for each of these specific setups. And it's hard to expect one single algorithm or one single type of analysis to work out well for all these settings. So in today's talk, we will be focusing on two specific multi-agent RL problems. First is two-player zero-sum Markov game. This is a classic problem. There are many existing works that study this problem, but usually they're not doing so from a optimization perspective. We look at this problem purely as an optimization problem, and we design a gradient-based algorithm to solve the problem. So we'll start by talking about why this problem is challenging to solve, and what are some of the structure we can leverage to design a good algorithm. Eventually, our algorithm will show this is an efficient algorithm that provably converges to the Nash equilibrium of the two-player zero-sum Markov game. And Nash equilibrium is a notion of a very strong notion of global optimality. Second part of this talk, we will shift focus a little bit in the beginning. We'll start by looking at not multi-agent systems, but single agent. We look at the policy optimization problem in single agent reinforcement learning, and we show the objective function has a structure. It's connected. We'll define, I'll tell you what exactly I mean by connected functions. But basically, it just means the super level set of the function is connected at all levels. And this is true under two policy parameterizations. And as a result of this connected super level set, we can derive a minimax theorem for robust reinforcement learning. In a robust RL, the setup is basically there is a learning agent and there is an adversary that wants to attack the learning agent. So in some sense, there's computation going on as well. Okay, so before we get into the mathematics of two-player zero-sum Markov game, I'd like to show you this diagram on the dynamics of two-player Markov game. This is a iterative process. In every iteration, indexed by k, the key components of the Markov game include state, action, reward, and transition. So state is literally just the the state of the environment. It's the sort of information on where the agents are in the system. Both agents observe the same reward. Observe the same state, but they make different actions. Actions we denote those by A and B, and they're sampled from policies, which we denote by pi and phi. So policies are just probability distributions. Once the agent takes an action, they receive a reward. I want to note the reward function for these two agents. First, they're different, and also both agents' reward function depend on not only its own action, but also the action of its opponent. And if R1 is exactly the opposite of R2, the sum up to 0, then the setting is called a two-player zero-sum Markov game. Otherwise, it's a two-player general-sum Markov game. The actions collectively will have an effect on the environment to make the environment transition to the next state. And the transition is so you have this sk plus 1. This is sampled according to a certain probability that depends on current state and two players' actions. This is a framework for modeling sequential decision making. So the goal of each agent is to collect as much cumulative reward as possible from the environment. Okay, mathematical formulation for this, as we said, two players observe the same state space, but they have different action spaces, and also transition happens. Transition kernel depends on current state, and action of two players. Reward function. So we'll be focusing on the zero-sum setting. So we can just characterize everything just with a single reward function. Agent 1 receives this reward. Agent 2 receives the negative of this reward. Given two policies, pi and phi. So first player takes policy pi. Second player takes policy phi. You can measure their cumulative reward, how much reward they collect in expectation. The expression is right here. And inside the expectation, there is also this discount factor gamma, which is a constant between 0 and 1 to sort of reflect the future reward is discounted by this factor. The expectation is taken over that dynamical system we just saw. Actions get sampled from the policy, and transition gets sampled from the transition kernel. So agent 1 wants to maximize this reward. Agent 2 wants to minimize it. So valid problem that agent 1 wants to solve is this maximum problem, right? It's looking at, well, it wants to find a policy that maximizes its own reward, supposing the second player takes the most adversarial response. And second agent wants to solve this min-max problem, right? It wants to maximize negative of j, so minimize j. Also supposing first player takes the most adversarial or best response. In general, max-min is smaller than or equal to min-max. But using the structure of Markov game, it is pretty well known that Nash equilibrium exists for this problem. So you have max-min equals min-max. And there is this at least one policy pair, pi star, phi star. We call this Nash equilibrium that attain this saddle point value function. Okay, if you're familiar with RL, there are essentially two types of algorithms for solving policy optimization problem. First type is value-based method. So Q-learning is example of value-based method. Essentially, you try to track the value function of the optimal policy, and then from the value function, you can recover the optimal policy itself. And the second approach is direct policy optimization. You treat the problem as an optimization problem, derive its gradient, just perform gradient descent or gradient ascent. Generalizing value-based method from single agent to to Markov game has been relatively better known. So essentially, what you do is, so this generalized version of this algorithm is called this approximate minimax value iteration. And the computational bottleneck for this is you need to solve a series of matrix games. And there are different ways of solving that matrix game, either by actual gradient or optimistic gradient algorithms, or there are like best response type algorithms to solve that matrix game. And the convergence rate of these value-based methods for Markov game matches up or almost matches up with the convergence rate for value-based method in single agent setting. So that's good. But for direct policy optimization algorithms, there is a gap. So probably the most straightforward gradient-based algorithm for Markov game is gradient descent ascent, right? This objective function has two variables, right? So it's just, you just keep track of two variables and you update them iteratively in an alternating fashion. Fix pi, update phi using gradient descent. Fix phi, update pi using gradient ascent. This algorithm looks super intuitive, but it's actually hard. It's very difficult to analyze. And big reason for that is the objective function is not very structured. It doesn't have like any strong structure. It can show this problem is non-convex-nonconcave actually. But good thing is there exists a gradient domination condition for this problem. I don't want to get into too much details on this, but essentially if you fix second player's policy, look at the problem as a policy optimization problem with respect to the first player, then you can upper bound the optimality gap by something that measures the norm of the gradient. And by utilizing this condition, there is one previous work that shows gradient descent ascent does converge to the global Nash equilibrium. But the convergence rate is pretty crude. So this work shows the convergence rate is polynomial in all the involved parameters and also polynomial in K. But by looking at their choice of step sizes, the convergence rate is at least worse than 1/k to the 1/10 or even worse. Okay, so the aim of our work is to use direct gradient-based algorithm to solve two-player zero-sum Markov game, but we want to get better convergence result. And our approach to sort of the challenge of not having enough structure in the Markov game is we add structure to the game by introducing a specific regularization. And we hope the structure helps you solve the regularized problem fast enough. But the caveat here is, okay, if you add regularization, you also change the optimal solution, right? So you need to be very careful with how much regularization you add. And the specific regularizer we add is sum of two terms, and they're symmetric. First term is regularizing pi. Second term is regularizing or minimally regularizing pi. Second term is minimally regularizing pi. And this is no more than just a discounted, cumulative, and weighted version of the entropy of the policy. So if you just aim to maximize the first regularizer itself with respect to pi, the optimal solution, or one of the optimal solutions, is to make pi a completely uniform distribution. And same for phi. If you just aim to maximize the second term with respect to phi, maximizer is completely uniform distribution. So when you add the regularizer, add the first term, subtract the second term to the value function, then the effect is it makes the solution of the regularized problem more uniform. So in some sense, it's encouraging exploration. And we use this J subscript tau to denote the regularized objective function and the regularization weight tau. And if you can rewrite this value function and you can group these three terms together. And this almost looks like the standard value function for MDP and the modified reward. But I'd like to point out that this is actually not a valid reward function. Reward function is supposed to depend on state and action, but not on the policy itself. So this is policy dependent. And because this is not a valid reward function, a lot of what we know about Markov game doesn't apply right away. So for example, it's not even clear whether a Nash equilibrium would exist for the regularized problem. So the first step is, or the first thing we did was to show actually Nash equilibrium does exist for the regularized problem, and actually it's unique because of the regularization. And we use pi star phi star subscript tau to denote the Nash and the regularization weight tau. Okay, so adding regularization as structure to the problem, and here we like to discuss two important properties. First property is the distance between the regularized Nash and the original Nash can be upper bounded by something that's linear in tau. So this is good because if you solve the regularized problem and tau is small enough, then you're not too far away from the optimal solution of the original problem. Second structure is this subjective function satisfies something that resembles the PL condition under the softmax parameterization. So softmax parameterization basically is, so policies are like just you can think of those as giant matrices, but there is a constraint on the policy, right? So for each state, actions need to sum up to 1. Another way of representing the policy is to keep this parameter theta, which is the same dimension, but there's no constraint on theta, and theta encodes the policy through the softmax function. One benefit of doing this is turn the problem from constrained into unconstrained, but also sometimes they're only structure with respect to policy parameter, but not the policy itself. Okay, so going back to this, the structure on the problem is, again, they're symmetric. First is with respect to theta. Second is with respect to second agent's policy parameter. This is right. So on the left hand side, you're saying you fix second player's policy, looking at the gradient with respect to the first player. You can lower bound this gradient by this is the optimality gap when you fix second player's policy. And so for now, disregard these two terms. If you do not have these two terms, this is exactly a PL condition. Or if these two terms are constant, this is exactly a PL condition. And PL condition is this structure a lot of people consider in optimization community. It can be used to derive faster convergence rate for gradient-based method. Okay, but here I want to note, our condition is weaker than PL condition for two reasons. First is this coefficient tau is not a constant. As we said, we need to very carefully choose tau, because tau controls how much regularized problem is away from the original problem. Eventually, we want to solve the original problem, so tau becomes 0. But if tau is 0 here, then this becomes a useless bound. Second difference is the second term right here depends on the smallest possible entry in the policy. And if later on in the analysis you plug in this condition naively into the derivation, then one assumption you have to make is the policy entry for all the policy iterates of that gradient descent ascent algorithm needs to be bounded away from 0. But that's a very strong assumption to make, right? It's also hard to verify. You're analyzing the algorithm and you're making assumptions on the iterate of the algorithm itself. So that's almost a chicken and egg problem, something we want to avoid. And one important technical contribution of our work is we transform this assumption on the policy iterate to an assumption on the Nash equilibrium. We'll talk about that later. But essentially, that's an assumption on the structure of the problem itself. So at least it's something you can verify. And mainly by using the two structure I talk about, and also there are some regularity conditions we have to derive. Using those conditions, you can show if you fix the regularization weight, this very simple gradient descent ascent algorithm does converge to the Nash of the regularized problem, and the convergence rate is this is linearly fast, exponentially fast. Here, I want to note the convergence metric might be a little bit different from the convergence metric considered in some of the existing works. This is asymmetric. This delta pi measures the convergence of first player, and this is saying this is measuring the performance of the first player when the second player takes the most adversarial response. But second player's convergence, this delta phi, this is measuring the convergence of the second player when the first player's policy is fixed to its current iterate. So you see that this asymmetry in there. Both of these two terms are non-negative And when they're exactly equal to 0, that implies the policy iterate is at the Nash equilibrium. Yes, please.
So these two terms, are they upper bound?
Good question. What we know so far is when this is 0, this is at Nash, but it doesn't translate. Hopefully you will, I mean, it's good if this translates linearly to Nash cap, but we don't have that result so far.
So alpha, beta are otherwise different.
No, so in this case, they're otherwise they're the same. They're both actually they're both, I think they're both constant in this case. So not decaying over time.
And also, in your previous slide, there's a given entry of the policy. You showed that it's finite, but it's not so large. So for example, it depends on your data, right? Because data
Yes.
is bounded, then it's for now.
Right, exactly. So if when you add, so far we're only talking about regularized problem. Regularized Nash is always lower bounded, and is lower bounded by something that depends on tau, even though that dependency might scale exponentially, even though that dependency might scale exponentially in tau. But for a fixed tau, if tau is not going to 0, then you know the Nash is they have lower bounded entries.
I have that problem.
Cool. Right. And right, I'm hiding exactly the exact expression for eta, but I want to note this depends on tau and the step size parameters and also cardinality of the state space. Okay, so that was just sort of think of it as an intermediate step. Eventually, we want to solve the original Markov game, and the way the intuition behind this is very simple. We want to solve the regularized problem as the regularized problem dynamically approaches the original problem. So we choose, the only difference here is we make tau decaying sequences as well. And we choose both the step sizes and also tau as polynomial functions of time. And the important question here is how do you decay or how do you choose these step size parameters? There is important trade-off on tau, right? So if tau decays too fast, then regularized problem approaches original problem fast. But the efficiency of solving the regularized problem is not good. And we show, by properly choosing the step size parameters. We'll see that in a second, what the exact parameters are. And also, we need to make an assumption on the Markov game. We'll also see this assumption in a second. Under those assumptions, and their assumptions and properly selected step sizes, we can establish that this algorithm converges with rate 1 over k to the 1/3 to the Nash, and convergence metric again is asymmetric. And this is with respect to the original. This is to the original Markov game. There's no tau in this, so this is original Nash. And comparing this result with the state-of-the-art analysis for gradient descent ascent without regularization, there is a pretty large improvement in convergence rate. And this is exactly what that assumption needs to be. I'm assuming there exists a constant C that lower bounds the Nash equilibrium policy pair entry-wise, and this C needs to be independent of tau. So since adding regularization is making the Nash equilibrium essentially more uniform, this assumption is saying for the original Markov game, there needs to exist at least one Nash equilibrium that's completely mixed. That's essentially the assumption we're making. So we are working on trying to relax or remove this assumption. But something I'd like to note is, in some sense, completely mixed Markov games are the harder problems to solve. The difficulty of solving Markov game exactly lies in the fact that when you update one player's policy, the other player's gradient can change signs depending on, when you're updating the second player, its gradient depends on how the first player's iterates is what the first player's iterates is right now. But for example, if your Markov game has deterministic solutions, usually the the gradient doesn't change direction. The signs of the gradient doesn't change signs regardless of the iterate of the other player. And they're just converging regardless of the other player. In some sense, that's easier to solve, and it's exactly because Markov game is mixed, has this mixed national equilibrium. There are like difficulties with and when you actually run algorithms in practice, you see oscillations if you do not have regularization. I do not want to get into too much details on this, but I have a figure later on if anyone's interested on like visualizing the performance of this algorithm for completely mixed Markov games and not completely mixed Markov games, and showing why we believe this problem is a little bit harder to solve. Okay, and here I'm showing the exact choice of the step size parameters, alpha, beta, and tau. It turns out, interestingly, beta is actually a constant, or should be the optimal choice for beta is a constant. Alpha decays the fastest, and tau decays with rate 1 over k to the 1/3. Compared with state-of-the-art analysis for the algorithm without regularization, first we have better convergence rate, and second is in this previous paper they didn't show last iterate convergence. The convergence is established on the average of all the history iterates. But for some reason, for people in this community, last iterate convergence is considered more preferable, and we do have last iterate convergence. Okay, please, Siva.
So in first example, the regularization you have geometry.
Yes.
And here there is no noise.
No. Yeah. Exactly. Deterministic.
I'm surprised why you don't have geometry. So I know in the first one you're going to the wrong answer because of regularization.
Yeah.
So suppose let's say I give you an epsilon and I want to go with an epsilon on the correct answer. Find the regularizer so that the fixed point of that, the set point of that is within the epsilon of the correct answer. And then you can get geometry.
So
it has to do with the small circuit.
Right. Well, yeah. Actually, right. It has to do with this. With this tau. If there's yes. So right. So the problem is coming from this tau. If there's no tau, if tau is a constant, then or if it doesn't depend on tau, then as you said, you can get better convergence rate.
So in the single agent setting for policy gradient kind of algorithms. Okay, I think I know. You're using gradients. You're not using. So okay, so it's a line of work.
Yeah.
This one work by George Lamb.
Yeah, yeah. Right.
They do regularization.
Yes. Yes.
And the deterministic setting, they can get geometric convergence.
Right.
And stochastic, they can get the right.
Yes.
But you can get that only if you do mirrorism, not gradients. Or in other words, you should do natural policy gradient.
Right, and also right, but even if you do natural policy gradient, first thing is right. So you need to set up this condition that captures the. You need to set up a similar condition that resembles this when you do this is gradient, right? You need to do that for natural policy gradient, and also even if you do that, it's not clear. I mean, you probably cannot get rid of the tau. Right. Yeah. Yeah. Exactly.
But we have follow-up work that actually where we show that you don't even need to do regularization. Just take the vanilla objective and do natural policy gradient, and then you'll get geometry.
Right, for single agent.
For single agent.
Yes,
yeah.
yes, right.
So unless there is something I'm missing because of multi-agent, I would expect similar behavior.
That doesn't work. There's a recent paper. They did that. They have 1 over t.
Oh, that is what you're talking about? That doesn't
I think it's a different thing. But there is.
They did what? They did
natural policy gradient. I mean, everything else. Except the policy with regularization.
So the reason we do it's getting technical, but the reason we do policy gradient is when you have two agents, sometimes you need to be able to bound this term, the gradient of this with respect to theta, by the gradient of this with respect to psi. And you can only do that. I mean, we know how to do that if you're handling gradient. But if it's natural policy gradient, then that's get very complicated.
So if you do minimax value.
Yeah. Yeah. So as I said, I would classify that as a value-based algorithm. You do have better convergence if you do value.
You have geometry minimax should work for national policy. That's the intuition. I mean, for us, before we got our result, that was my intuition. Like, because policy iteration has very fast convergence, NPG without regularization should have geometric convergence. That turned out to be true. But here, and it turns out that in simulations, I think policy gradient is actually not the right. The many issues with the negative.
Right. Yeah.
But national policy gradient is right.
Right. So we do right. So I did think about like generalizing this work to or like extending this to like. Right. It will be using different structure of the game. Yes, exactly. But thanks for the comment. Cool. And then second part of this talk is we look at policy optimization problem in infinite horizon average reward MDP. So same dynamical system, but we're looking at, so the objective function now is it doesn't have this discount factor. It's just summing up the reward divided by how many iterations you have. So this J is our objective function, and I want to stress this dependency of J on the reward function. I'm stressing that I'm having this subscript R because this later on will play a role in its application to robust RL. Okay, I'm defining a few quantities to re-express the cumulative reward. So given a fixed policy pi, you can compute the transition probability matrix for the state. And this transition probability matrix incurs a stationary distribution over the state. We denote this by mu pi. Under the ergodicity assumption, so if the Markov chain is ergodic, then mu pi is the unique eigenvalue, or mu pi is the unique eigenvector of p pi with eigenvalue equal to 1. And you can also define the stationary distribution over state and action, and that's just the product of mu pi and the policy. You can rewrite the cumulative reward as the inner product of the reward function with mu pi. So so this objective function is linear in R and also linear in the stationary distribution, but it's nonlinear, non-convex with respect to pi. And when I say policy optimization problem, this is what I want to solve. Find the policy that maximizes this term. Okay, I was sort of repeating the story here. So we want to show the super level set of this objective function is connected. So first I want to define connected set and super level set. Mathematical expression is here, but conceptually this is very simple. All the three figures are showing examples of connected set. Basically, you just need to check. You take 2 points on the set, and you want to be able to draw a line connecting those 2 points. This line needs to be continuous and also needs to be completely contained in the set. If you can draw the line for every 2 points in the set, then the set is connected. Okay, and super level set definition is also very simple. So function f of x, super level set at level lambda is the collection of all the parameter, or all the x variables that produces a produces a function value larger than or equal to lambda. Okay, and we say a function is connected if the super level set is connected for all lambda. Also want to introduce this notion of equiconnected collection of functions. Again, conceptually this is very simple. It has 2 requirements. First requirement is, okay, so consider this function f that has 2 variables, x and y. We say this function is equiconnected with respect to x if you fix you fix y, if the function is connected for all y, for any y. This is the first condition. Second condition is, when you show this function is connected, you have to show the super level sets are connected. So you have to draw all these lines. Second condition is saying the way you draw these lines should not be affected by y. So, or more rigorously speaking, there should exist one way of drawing the lines that works for all y. I'd like to take a break and see if that's clear so far.
The function values change. The points you need to connect are changing. How can the paths be?
Good question. Right. That's a good question. Well, I guess this is a better way to describe this. Given any 2 points, you want to be able to draw a line so that along this line, the function value changes gradually from the function value of the first point to the second point. And regardless of what level you're looking at. So you should be able to draw this line that's true for all y, such that the value is transitioning between the first and between these 2 points. So in some sense, it's not really looking at the level, but it's saying you need to be able to interpolate the function value of these 2 points.
So say that, okay, I have a point here. There's a path. So we have all these different super level sets. That path is a level set. Right, every point along the path is
every point along the path is in the super level. That's true. Yeah.
That's sort of what. So there is some path.
And thanks for the question. So this is stronger than just requiring functions connected for all y. Okay, and our result is, okay, we look at the super level set of this function of that value cumulative reward, which is just a collection of policies that produce a value function larger than or equal to lambda. And we show, so first we show this is a connected set for all lambda. And second, the collection of functions. So this function with respect to function, this function has 2 variables, r and pi. This is equiconnected with respect to pi. And so I mean, we talk about this equiconnectedness only because of an application to Minimax theorem later on. So once we have this condition, we want to think about how this is different from one of the most important structure in that has been established in existing work for policy optimization, which is this gradient domination condition. You're upper bounding optimality gap by the norm of the gradient. And this implies every stationary point is globally optimal. So we want to see, which condition is stronger, or does one condition imply the other? And it turns out neither condition implies the other. And you can construct examples showing. So first figure, this is an example function that observes the gradient domination condition, but it doesn't have connected super level set. And second figure is an example that has connected super level set, but it doesn't observe gradient domination condition. So in some sense, both conditions are characterizing the optimization landscape, but from slightly different perspectives, even though there's definitely overlap. Okay, and we can, so that was for tabular policy setting. You can extend this argument to a neural network policy class as well. So so this is showing the pipeline of getting an action from a state when you use neural network as the policy. And say you start from the state is just in this Go chess game is just representation of the board. First thing you do is you extract a feature vector. Usually this way of extracting a feature vector is human design. If you do not have good knowledge, you can always just take the pixel wise representation, or actually the grid wise representation of this board. Or if you want to put in some other information, for example, how much area you occupy, or like what is your expected chance of winning, you can do that as well. And once you have the feature vector, you feed that into the neural network. Neural network can have arbitrary length or width. But the important thing here is the last layer is dimension needs to match the cardinality of the action space, and you put softmax function on the last layer, and so that you can interpret the output as a valid probability distribution. And then that's basically the policy in state S, and then you can sample from that policy to get actions. Here, what is the parameter? Parameter is the collection. We use theta to denote this. This is a collection of all the weights and biases of the neural network. And I'm using omega to denote all possible weights of choosing these weights and biases. So for our analysis later, we need to make two assumptions on the structure of the neural network. First is the activation function needs to be invertible, and also we need some regularity condition on its inverse. And the commonly used activation functions that observe those conditions include leaky ReLU and parametric ReLU. It's basically piecewise linear. And of course, you need to have softmax activation function on the last layer to produce probability distribution. Second assumption we're making is neural network needs to be sufficiently over-parameterized. Specifically, the specific assumption is first layer is wide enough, and the width of the neural network is decaying over layers. And then, I mean, now this objective function essentially becomes a function of the policy parameter theta, and you can define this function with respect to theta. And again, we show a similar story here. We show the super level set, which is a collection of the policy parameters. This is again a connected set, and also it has this equiconnected property as a function of both reward and theta. Okay, and this result has an application in robust reinforcement learning. I'd like to say there are many different formulations for robust RL, but usually the key ingredients that are always present include a learning agent and one or more adversary that wants to attack the learning agent. Sometimes the attack takes the form of a modification to the reward function. Sometimes the adversary plays a two-player zero-sum Markov game with the learning agent. So it can modify not only the reward, but also the transition. Our formulation we consider in our work is adapted from, or actually is exactly taken from this recent work in 2022 from a group of researchers at University of Maryland. And in this formulation, the adversary can only attack the reward function. And the specific setup is this. So first of all, there is a standard Markov decision process, and there is a learning agent that wants to find the optimum policy for this MDP. Say the optimum policy is denoted by pi star. The adversary has perfect knowledge of the MDP, and it also has this target policy pi dagger. And the goal of the adversary is to modify the reward function to make the learning agent adapt pi dagger eventually instead of policy pi. And that boils down to solving this optimization problem. So objective function, this is saying you want to make, so R is the original reward. R prime is the candidate attack reward. This is saying you want to make the minimal changes to the reward function subject to so this is saying pi dagger needs to be the optimal policy under that modified reward. And epsilon dagger is a non-negative parameter that the adversary can choose. So I mean, it's perfectly fine to set epsilon equals 0, but if it's non-zero, this is saying pi dagger needs to be the unique optimal policy. Okay, so that was the attack model. The learning agent is aware of the attack and wants to defend against the attack. The question is, how does the learning agent do that? Well, we need to be clear about what the learning agent observes. It only observes pi dagger, the attack, a poison reward, but it doesn't observe the original reward, even though it wants to perform well under the original reward. So one strategy of defense is you maximize your performance in the worst possible case, in the worst possibility of the original reward. And that becomes right. So and that's equivalent to solving this optimization problem. So this inner minimization problem is trying to figure out what is the worst case of the original reward. Constraint here is this is saying R dagger needs to be an optimal attack for R prime. Is this clear so far? Okay, good. And the important structure of this problem is if you fix the reward, this reduces to a standard policy optimization problem. If you fix the policy, this is trying to figure out that optimal attack, or well, no. This is trying to figure out that optimal, not optimal. This is trying to figure out that worst case, original reward, worst case possible original reward, and objective function is so the decision variable is R prime. This objective function, we saw that this is inner product of R prime and the stationary distribution. So this is linear objective function. You can show the constraint set is convex. So this is a convex program. And go ahead. Yeah, so this objective function is a function of two variables, right? I'm saying if you're not solving the maximization problem, just just plug in a certain policy for this. Just look at the problem with respect to the other variable. What structure does it have? And then then I fix R and look at what problem does right? You fix R, then you remove this constraint, you remove this minimization. What does the problem? What structure does the problem have? Right. So, and because of our earlier result on connected super level set or equiconnectedness, we know this function is equiconnected on one side and convex on the other side. Right, because this is a standard policy optimization problem. Then there is a classic result from the literature that shows every function or any function that's strongly convex on one side and equiconnected on the other side observes the minimax equality. So max min equals min max. In general, it's just this is supposed to be less than or equal to. Okay, so we just plug in our result from equiconnectedness. We're able to conclude that minimax equality holds for this robust reinforcement learning problem. This formulation, so formulation for this robust reinforcement learning problem is proposed in that earlier work, but it's unclear, or they were not able to establish this that existence of Nash equilibrium or minimax inequality. So we're the first work to derive this result. Okay, and remember everything. I mean, so this is for tabular setting, but this connectedness, equiconnectedness also holds under neural network policy representation. So you can derive a similar version of this for under that neural network policy setting as well. Okay, I think that pretty much concludes the talk. The presentation is based on two works. First is in last year's NeurIPS. The other is under submission right now. Cool. Thank you. Yes, please.
So the equiconnectedness follows that view. So you said that this is analogous to gradient dominance. So can you use it to get global luminosity?
That's a great question. We are so we're working on this. We're looking for applications of equiconnectedness, and so far this application minimax is only being found. Gradient domination in terms of algorithm design is, I would say, it's more useful. Like that, just to gradient descent, then like that allows you to do this good optimization. This connected super level set is not super clear what application it has. But something we had in mind, though it's taking a while, is we try to solve multitask reinforcement learning. In general, if the dynamics of the problems are different, then there may not exist. Then there is no gradient domination condition. So gradient descent doesn't necessarily converge.
In which setting?
Multitask setting. If the dynamics are different. But if one interesting setting is under neural networks policy representation, there could be these multiple tasks could have the same minimizer, or the set of optimal solution could overlap at a certain point. We were trying to think if this could inspire any algorithm design for that problem. So maybe you solve one problem, so you can figure out optimal solution set for this problem, and then like in that solution set, you try to figure out the optimal solution for the second problem, and then you sort of do this. But it's not clear like what other applications of this work is.
Thanks.
Great question.
Everybody, please feel free to take your food before you get started.
We're good. Okay, so thanks again, Sihan, for coming. And next week we actually have two seminars, one on multi-arm bandits and the other one on sort of GANs from Austin Shu, if you know him. So yeah, right.
We have another virtual seminar on